Swayam Prabha. Digital India. Educated India.
Last class we were talking about Martensitic transformation. We talked about the crystal along A and B axis. This total is the actual Martensitic transformation. So, austenite to martensite transformation, if you say, it is a combination of these two. Depending on to what extent this process, second process can occur, he is going to decide what is the C by A ratio. Just after shear, C by A is 1.414, we have seen, and in principle it would like to come to 1.0, which is the BCC structure, which is a stable structure at room temperature. So, it would like to come from there to here, depending on the carbon content present in the alloy and depending on what is the extent of compression that can take place along the C axis. This would come towards this. If there is no carbon, it would in principle be this. So, this is what is the whole structural. Let us now look at the thermodynamic aspects. Where is the driving force coming from? We have already seen that at room temperature, if I quench a austenite, if I take an austenite and then quench it, the stable structure is BCC, am I right? At room temperature the stable structure is BCC. So, austenite wants to transform to this BCC structure, that means the FCC structure wants to transform to this BCC structure, that is the whole process. But in principle under normal conditions FCC can transform to BCC structure by a polymorphic transition involving what kind of a diffusion? Short range diffusion. In principle FCC to BCC transformation can happen by a short range diffusion, but because you are at a temperature where short range diffusion is not able to happen, then you see a shear taking place. So, if I draw the free energy versus temperature diagram, you would see a transformation something like this. At higher temperature it is the gamma that is stable, at lower temperature it is the martensite that is stable. Martensite in principle it could be a BCC martensite or a BCT martensite depending on the type of situation. So, there is a temperature which we call it as the T naught for this gamma to martensite, but actually the transformation never occurs at that temperature, because the transformation needs some shear. You need a certain shear to occur inside the material, so that you would see the gamma transforms to martensite. If there is no shear, gamma would not transform to martensite, and this shear, for it to occur you need to provide certain driving force for the shear to occur. As a result, actually the transformation occurs at a temperature below this, at some temperature which is what we usually call it as the MS temperature, which is actually below the T naught. This is the extent of undercooling that you need from the T naught to be able to have the transformation, and this MS temperature we all know is dependent on a number of factors. One is carbon content and the other alloying elements present, and also the grain size. For example, grain size can also control the MS. So, there are many factors which will shift this temperature to a lower temperature and avoid transformation at the T naught. When do you have actually the transformation occurring very close to T naught? When the extent of shear that is required for the transformation is very small. in any particular system where the extent of shear that is required, the shear stresses that need to be provided for the shear to occur, if that is very small, then you can say that in principle Ms comes close to T naught. Otherwise you would always see some temperature which is below this T naught where the transformation occurs. This is where we need to understand the influence of stresses on Martensitic transformation. We always say there is something called stress induced Martensite. You have heard of it? Hatfield steels is one of the wonderful examples of it. You take an austenite and quench it and get the austenitic structure and deform it, and you would see during this deformation this austenite transforms to Martensite. But the reason why you see austenite transforming to Martensite during deformation which is what we call it as deformation induced Martensite, and we even give a temperature called MD temperature for that temperature where the Martensitic transformation occurs during deformation, and usually this MD is always greater than Ms. The reason is that whenever you deform a metal, there is always shear stresses which come into the picture, whether you do tensile deformation or you do extrusion, you do wire drawing, most of the processes excepting one deformation process which is called isostatic compression. For example, if you have heard of hipping and sipping, if I do hipping, for example, I have a isostatic hot compression, or sipping cold isostatic compression. So when you do isostatic pressing, that means you are not inducing any shear stresses inside the material. The moment you do not induce any shear stresses in the material, the Ms would actually go down. The moment you have always some shear stresses which get induced into the material during deformation, then you would see the Ms will be higher than that. That basically means that you would see that the gamma transforms at a higher temperature to Martensite rather than a lower temperature. The reason is whenever I apply a stresses inside the material, shear stresses, the gamma which is the parent phase will have a higher free energy when compared to the original gamma which is undeformed. A deformed gamma will always have a higher free energy, and if I use that, let us say I use a different free energy curve for that. Now this is, call it as deformed gamma, gamma which is deformed will have a higher free energy than the normal gamma, then obviously you will see at some temperature it has to intersect, either we have to make this or change the Martensitic curve, whatever it is, and if that is the case you would see another temperature. Now the intersection has happened at a higher temperature, that means the T naught has shifted to a higher temperature. The austenite would transform to Martensite at a higher temperature. If the T naught is shifted to a higher temperature, then obviously the Ms also will shift to a higher temperature. So you would see that the austenite deforms to transforms to Martensite at a higher temperature, which is what we call it as a MD temperature, when you have deformed. But now how do I understand about the other aspect? If I subject austenite to a compression, isostatic compression, then the situation is different. Then the situation is, if you look at any time any material, if you subject it to a compression, that means you are trying to reduce the volume, you are compressing it. Whenever you are compressing it, the phase that is always stable is a phase that occupies less volume. This is always the case. For example, if you want a graphite to transform to a diamond, you need to apply a compression and also a higher temperature. So, a high temperature and compression would make a graphite form, and the higher the pressure that you apply, the lower the temperature at which the diamond would form from a graphite. So, the reason is diamond is a much more close packed structure than a graphite. So, whenever this is true even for any liquid to solid transformations, if you take a liquid to solid transformation, if you take a liquid which is trying to transform to a solid and you apply a compression on the liquid, some kind of a isostatic compression, you would see the phase that gets stabilized would be the phase which is always the having which can occupy a lower volume. Usually in most of the cases solid occupies the lower volume. So, solid becomes stable. Solid becomes stable means what should happen to the melting point? It should increase. Okay. So, whenever you pressurize, is basically Clausius-Clapeyron. So, if you go back to the Clausius-Clapeyron, whenever I apply a vacuum, you would see that because the pressure is reduced, at a reduced pressure you would see the melting point occurs at a lower temperature. Whenever I apply a pressure, you will see the melting point will be higher, the solid melts at a higher temperature, or the liquid does not solidify at the normal melting point, but it will solidify at a higher temperature. Okay. So, the melting point would go up when you apply the pressure, excepting in the cases where the solid occupies more volume than the liquid. Okay. When the solid, that is examples of like water to ice transformation or any other transformation.
But in terms of free energy effect, whether it is a tensile or compressive.
Correct. This is an important point. So, now if I look at it in terms of stresses, any stress in principle should raise the free energy of a system. So, that means the stresses would definitely raise the temperature of the free energy of gamma, but because of the fact that the martensite is a more open structure than that of the gamma, the relative free energy changes will be such that the gamma free energy because of this pressure would actually go down with respect to the martensite when compared to what you have seen if there are no hydrostatic pressures. So, there is definitely going to be some raise in the free energy of gamma because of the stresses that are there, but at the same time the second factor which counteracts that is the fact that you are putting a hydrostatic pressure, and then you would see if you simply look at the Clausius-Clapeyron equation, which says that dt by dp is delta v by delta s or delta s by delta v by delta s, this and this. So, if you look at that, from that you would see that as the pressure is increased, if both are positive, T2 should increase, am I right? So, you would see, or if one of them is negative, you would see in our case if you look at austenite to martensite, if you look at the transformation, okay, V of austenite, V of gamma is higher than or lower than, it is lower than. So, it is lower than V of martensite. So, delta V should be equal to V of martensite minus V of gamma, that should be equal to positive. And if you look at the delta S part of it, okay, so S of gamma and S of martensite, if you look at it, which will be higher? Okay, gamma will be higher because it is a high temperature phase when compared to martensite. So, this is higher. So, delta S will be negative now, S of martensite minus S of gamma, that will be negative. So, one is positive, another is negative. So, this is going to be negative, the ratio. So, the higher the pressure, the temperature should be lower, and if that is the case, you would see that effect will come into picture, and as a result you would see this would have a overall in fact of reducing the free energy of the gamma in such a way that the T naught curve shifts to a lower temperature. So two types of pressures, two types of stresses can lead to two different effects. One which is a compressive stress, which is a isostatic compression, can lead to a lower MS. If you apply, I mean nobody does this for an austenite, nobody has done, I mean excepting in case of powder metallurgy people have done. If you take a powders of let us say austenite and then do a hipping of it, because isostatic pressing is usually done only in powder metallurgy, otherwise you do not use it in case of normal steels which are produced by casting route and then deformed to give whatever shape it is. You go through all other processes such as rolling, forging and other deformations, but you rarely use a kind of isostatic pressing. Isostatic pressing is more in terms of powder metallurgy. So in case you take iron powders in a at a iron or steel powders in the gamma state and then do a hipping and then you quench it and you compare it with another steel which is produced by a normal case, you would see that the Martensite transformation occurs at a much lower temperature when compared to a normal steel. So only in such case you can actually confirm that, and under normal steels we do not need to use hipping at all. So it's this is of more concern for powder metallurgy people. Okay. So in case you are dealing with powders and then doing hipping or sipping of them, then trying to see whether I get a Martensitic transformation, you may say why should I bother about what temperature it will transform. I need to bother about it because I need to know to what temperature I should bring it, so that if I want to get 100% Martensite. So if MS itself is low, MF will also be low. So for you to be able to get 100% Martensite, you need to go to a much lower temperature, sometimes maybe even a sub-zero. So that is an aspect which you need to understand. So the pressure brings in this effect and that changes the free energy, and as a result you would see the whole transformation changes. Okay. So this is another aspect which regularly people do not talk about it. People always say deformation will lead to an increase in the Martensitic temperature. That deformation is only a deformation which induces shear. If there is no shear, it is induced inside the material, and it is only a deformation which is just a compressive deformation, you would not be able to see that. Okay. I think with that we will close Martensite. I think we have more or less talked everything about Martensite, including the crystallography aspects of it. I will not go too detailed into the kinetics of it. Yeah. Yeah, thermodynamics will be similar, excepting that you would see in some cases the shape memory effects, particularly in the non-ferrous nickel titanium, and those are related to whether you have the Martensite is a thermoelastic Martensite, what is the extent of the transformation strains that are involved, and also for example I do not know whether you have ever thought about it, why steel Martensite is not does not have a shape memory effect. You do not see shape memory effect in steels, though there is a Martensitic transformation. Less, anything more? One of the primary criterions for a shape memory effect is that the transformation should be reversible. Austenite to Martensite and Martensite to austenite should be reversible. For example, in a steel, typical steel, when I start heating the Martensite, what happens? It starts tempering, and then because of the presence of carbon inside, the carbon starts coming out in the form of carbides, and you do not see Martensite directly transforming back to an austenite. There are a number of intermediate phases that come into picture, isn't it? So you, unless you go back to the A3 temperature, you will not actually get the austenite transformation, whereas in non-ferrous nickel titanium and a number of other cases like copper base alloys, these are all reversible transformations, there is no other phase involved, and only when you have a reversible transformation you will be able to see the shape memory effect. So that is another thing. Of course, as he mentioned about it, the extent of strain is also important. You need to have a reasonably good amount of strain which can be able to be recovered during either heating or during deformation. So we will not go into the details of it, that is more of kinetics and not really thermodynamics, maybe in some other consideration we will see that. Now let us look at the other aspect, other type of transformation which we have not covered so far, is the order disorder. Before we actually go into the thermodynamics, let us look at how do we recognize this order disorder transition in a material. Whenever we say order and disorder, I think all of you are aware, when we talk about order, there are two types of order in a material. We talk of structural order and we talk of chemical order. So whenever I say this is an ordered material, we are usually using the term chemical order there. When I say structural order, then a structural order, it can be a crystal, it can be a glass or an amorphous, or it can be even a third one which is a quasi crystal. These are the three types of structural orders, and the differentiation is a crystal is one where you have both orientational symmetry and both rotational symmetry and translational symmetry, and this is where you do not have both, and this is where you have one of them. The rotational symmetry exists but translational symmetry does not exist. That is how we talk about it. When I say chemical order, first and foremost is it is structurally ordered. And it can be chemically disordered or ordered. There is no possibility of looking at a structurally disordered material and look for a chemical order there. And similarly again, when I say chemical order, we are again talking about long range chemical order. We are not talking about short range chemical order here. Short range chemical order and short range structural order will always be there in every material until you go beyond the beyond melting point, boiling point. When you are above the melting point, you still have a short range order, you still have a short range structural order. If that is a chemically also ordered, there may be a short range chemical order also inside the material. But if you go beyond the boiling point, there you have individual molecules and individual atoms, so you do not have a chemical order or neither a structural order. So whenever we are talking about order, this material is ordered, we always talk about long range order, we do not talk about short range order. That is, people have to keep it in mind. And when I am saying the long range order, so it is not possible to have a structural disorder and a long range order, these two will not go together. You cannot have an amorphous alloy which is chemically ordered, because it is already structurally disordered. So because it is structurally already disordered, there cannot be a chemical order inside. Chemical order, we always look inside the unit cell. The moment you talk about chemical order, that means how atoms are arranged inside the unit cell is what represents the chemical order. If there is no unit cell, there is no question of talking about how the atoms are arranged inside the unit cell. So as a result, because amorphous materials do not have a unit cell at all, so we will not talk about structural chemical order there. So chemical order basically implies a structural order. So, it is a subset of structurally ordered materials, that means it is a subset of crystals. So, chemical order or a chemical disorder are two sets inside a structurally ordered materials. So, if I consider first of all that it is a crystalline, that it has certain crystal structure, then I talk about whether it is ordered or disordered, and this question of ordered or disordered comes into picture again for the structurally ordered materials only when you have more than one element inside the material. If you have a pure metal, we do not talk of a chemical order obviously. So, we have only one element, means it is simply structurally ordered, that is it. You do not talk about chemical order. Chemical order comes into picture only when we talk about alloys more than one element. When you have more than one element present, then only we talk of chemical order. Then we talk about how each element is arranged inside the unit cell. If they are randomly arranged, if there is no preferred site for any one of the element, we call it as it is chemically disordered, and such materials are usually called as solid solutions or disordered compounds. In fact, it is very difficult to differentiate between a solid solution and a disordered compound. Both of them will have the two elements, if it is a binary alloy, two elements which are randomly present inside the crystal structure, whatever may be the crystal structure. So, a disordered compound is usually referred to as a solid solution, but accepting that, for example, if I am talking of a nickel aluminum alloys, when I take a compound such as Ni3Al, Ni3Al is a FCC based compound, intermetallic, with what we call it as L12 structure. So, here you have 3 atoms of nickel occupying the face centered positions and aluminum occupies the body corners, and now this becomes, let us say, disordered. That means inside the unit cell, if you have 100 unit cells, in 100 unit cells you would have 75 atoms of nickel and 25 atoms of, I mean, in fact it should not take like that. In 100 unit cells actually you have much more, because every unit cell effectively has 4 lattice points. Okay. So, if I take let us say about 25 unit cells with about 100 atoms, in these 25 unit cells the nickel atoms will sit wherever they want to sit, the 75 nickel atoms would sit wherever they want to sit, and similarly the remaining 25 atoms would sit wherever they want to sit. There is no preferred place for that. So, that means out of the 3 face centered positions, let us call them as half of half, I mean half of 0, 0 half half and half 0 half. If you consider these 3 positions, one of them may be occupied by aluminum, another may be occupied by nickel. So, there is no preferred a site for either nickel or aluminum, but the structure is still FCC. Structure is still FCC, excepting that aluminum and nickel are randomly sitting wherever they want, and that is what is a disordered compound. And if you want to call it as a solid solution also, that there is no problem in calling it as a solid solution, excepting that there can be a solid solution of aluminum in nickel with about 5% of aluminum, okay, or 10% of aluminum. You can't call it as a disordered compound, because it is not a compound at all, it is a solid solution of aluminum in nickel, excepting that this particular thing, if you want to call it as a solid solution, this is the one which will have 75-25 exactly. So, the composition would correspond to intermetallic composition, but the structure would correspond to a solid solution structure, clear. So, the composition will be exactly a stoichiometric composition like 75-25, but the structure will be a disordered structure, disordered chemically and ordered structurally. So, that would be the difference. So, there can be numerous solid solutions with different amounts of solute content, but the moment I say disordered compound, the disordered compound will have a stoichiometry corresponding to that particular compound. So, that would be the difference. Now, if I want to look at how do I find out this extent of disorder, when I take an Ni3Al and make it disordered, in principle if I take a Ni3Al and start heating and talk in terms of what is called order parameter, okay, they refer to it as L, which is a long range order parameter. Order parameter can change in two different ways. It can become like this, or it can become like this. This is 1 and this is 0. What do you mean by order parameter being 1? That means the probability of finding a nickel atom, let us say aluminum atom at the 000 position. What are the positions here in FCC? 000, half, half 0, 0, half half and half 0 half. These are the 4 lattice points, am I right? And 0 position is supposed to be aluminum in an ordered structure. These 3 are supposed to be the nickel positions. If the probability of finding aluminum at 000 is 0.25, then we can say it is perfectly ordered. That means out of the 25% of aluminum atoms inside the alloy, all the 25% atoms are sitting at this, okay. So, that means if you look at the probability of if you call this as A site and you call this as B site, if all aluminum atoms are occupying A site, then I call it as a perfectly ordered. If some of the nickel atoms are also occupied at the A site, then it is not completely ordered, okay, it is partially ordered. And the disorder can be when the probability of finding aluminum at the A site is 1, then we call it as L as 1. That means all aluminum atoms are there at this. If you see partially aluminum is sitting there, and when you say that the probability of finding aluminum at this A site is 0.25, if I call it as A site, if the probability P is 1 there, if the probability P is 0.25, then we will say L is 0. That means it is as if the total amount of aluminum is 25% and the 25% is sitting everywhere, and 25% of the aluminum atoms are sitting here. That basically means it is as if there is no preferred site for aluminum. So, if you find the probability of aluminum atoms sitting at the A site as 0.25, then we say long range order is 0. So, this is how we can find out, provided you know where the atoms are sitting, but it is not easy to find out where the atoms are sitting, but there is a indirect way we can find out the long range order by looking at the XRD patterns. If you take a perfectly ordered structure Ni3Al, let us say, which is perfectly ordered, which people have made, let us say, by some process, and do an XRD of it, and then find out what is the basic difference between the ordered structure and disordered structure. If you do an XRD, you get extra spots or extra peaks, which we call them as superlattice peaks, superlattice reflections. In case of FCC, what are the fundamental reflections? I am asking what are the reflections, you are telling me what is a square plus k square plus l square. 1 1 1, 2 0 0, 2 2 0, 3 1 1. What is the rule it follows? All should be unmixed. Okay. So that is how, as she says, this is h square plus k square plus l square being 3, 4, 8, 11 and 12. 12 is 2 2 2. These are what are called the fundamental reflections, that means allowed reflections. And what are the superlattice reflections? These are, I call them as fundamental. What are the superlattice reflections? You can have 1 0 0, you can have 1 1 0, you can have all others, whatever is not possible. Okay, for example, you can have 2 1 1, 2 1 0, 2 1 1, all of them which do not exist in this list. Each of them will have certain intensity depending on the structure factor associated with that reflection. Every reflection would have a certain structure factor which we can calculate, and in principle if one has prepared a perfectly ordered thing in JCPDS files, if you go, you can take any one of the peak and find out what is the intensity of it. And so basically take your material, find out what is the intensity of the 100 peak and take it as a ratio of the intensity with respect to the 111 peak, which is the most intense fundamental for your sample, divided by the I of the same peak for the standard, and take the ratio of this, and square root of that is what is called the long range order parameter. The reason why we take square root is the intensity is always square of structure factor. Okay. So square root of this, basically I am getting the structure factor with respect to my sample and the standard. Standard is something which is perfectly ordered. Anything, you can choose any peak, any fundamental peak and any superlattice peak. We choose usually the most intense fundamental peak. In a FCC the most intense is always 111. You always know that, for example in BCC the most intense has to be 110. As you go to higher and higher theta, the intensity goes down. If you have done XRD you will know this, and in addition only in certain cases you would see, for example 200 being more intense than 111. When do you see that? When there is a texture. If there is no texture inside the material, then in principle 200 and all others will be smaller than 111. So this is how we will see. So we choose the most intense here, and among these whatever is the most intense you can choose that and take the ratio of them. So you can choose any one of them in principle. In principle there are cases where you do not even choose 111. When do you not choose 111? Let us say, think of a hypothetical situation where I will not choose the 111 peak as the fundamental peak for finding out the superlative, I mean the long range order parameter. It is FCC, the phase is FCC. She says if it is not FCC, okay, that is a trivial point. It is still FCC, but I am not choosing 111. Why? When there is a second phase inside the material, if you have some other phase whose some peak of it overlaps with 111, then obviously the intensity that you are looking at that peak is a combination of the intensity coming from the 111 peak of your ordered phase plus some other peak of some other phase, unless you do what is called the deconvolution, and if the overlap is very good then you cannot even do deconvolution. If there is a small shift, something like this, then you can do a deconvolution. If the two peaks are not actually shifted at all, they are exactly falling one above the other, you cannot use that. Then you should go to some other peak which does not overlap with any peak of the second phase. That can be any peak. So you have to start looking where, as long as it is a single phase we choose the 111, as long as you have more than one phase we do not choose that. So anyway, so this is all about how to recognize this is ordered or disordered and how to calculate what is called the superlattice, I mean the long range order parameter. Now let us look at the thermodynamics of it. The moment we say it is ordered or disordered, we can talk about the free energy of the ordered phase, free energy of the disordered phase. Free energy of the ordered phase is H minus Ts, am I right? Similarly, I can also say here H minus Ts, where H of the ordered phase, S of the ordered phase, H of the disordered, S of the disordered. The moment I say this, when I look at the ordered phase, the entropy is always a combination of two entropies, thermal and the configurational. The thermal entropy will always exist in any material at any given temperature excepting at the absolute 0, but the configurational entropy for an ordered structure is 0. In fact, if it is a perfectly ordered structure, if L equal to 1, then the S is 0, because the number of ways of arranging atoms is 1. What is S config? Delta S config is K ln W, where W is the number of ways of arranging atoms. If the number of ways of arranging atoms is 1, then that is 0. So the configurational entropy is going to be 0. So in principle this particular term is going to be much smaller when compared to this term here. So as a result, if I now plot G versus T and also look at this too, H of ordered and H of disordered. Whenever we talk of a ordered structure A and B, when do you get an ordered structure? When omega is negative. Whenever omega is negative, whenever there is a strong attraction between A and B, you get an ordered structure. And so that means H of the ordered structure is always more negative than the H of the disordered structure. Disordered structure would not have the same bonding, so as a result, so here you would see the ordered structure there is more attraction between A and B, so this is a negative, more negative than this, so this is less than that. And similarly, if I look at S of ordered structure and S of disordered structure, S of ordered structure is also lower than the S of disordered. Once I know these two, I can actually talk about how the G versus changes with T. You would see two values of H here, H of the ordered will be lower, H of the disordered will be higher. I will put it on this side to solve the problem. And if I look at the how G changes as a function of temperature, G decreases with increasing temperature or increases with increasing temperature? Decreases. So now the question is the rate at which it decreases is going to be different for both of them. One of them which is having a higher entropy will have a steeper slope. So you would see that the disordered structure would go like this, the ordered structure would go like this. Because the S, which is the slope of it, so this is the S of the ordered, this is the S of the disordered. At any given temperature, if I look at the entropy, you would see that the disordered structure should have a steeper slope when compared to the ordered structure. If that is the case, you would see at some temperature these two will intersect, and that is what we call it as a Tc, what we call it as a critical temperature Tc, beyond which you would see that the disordered structure will be more stable than the ordered structure, and you would see an ordered structure transforms to a disordered structure. It is almost like a liquid solid transformation that we have seen earlier, exactly similar to that you would see this happening. Okay. So, you will only thing is then there are two ways in which it can decrease, that is what we call it as first order and second order transitions. There is one where the order parameter remains almost 1 up to the Tc and suddenly at Tc it changes to 0. This is something like a first order transition where you have sudden change in the phase structure at a particular temperature. There is a discontinuity. So, the solid remains as solid up to the melting point, suddenly at the melting point becomes liquid. It is not that the extent of disorder in the solid keeps on increasing and at the melting point it becomes liquid. It is not a continuous transformation, it is a discontinuous transformation. Whereas there are certain order disorder transitions which are continuous, where the order parameter continuously changes with Tc and finally becomes 0 at Tc. This is what is a second order transition, this is what is a first order transition. These are what are called continuous transformations. It is more of mechanism of order disorder, let us not bother too much about it, but as far as the thermodynamics is concerned we can talk about this. And obviously once I know this, at the transformation temperature I can equate these two, am I right? So, once I equate it, H naught minus T into S naught is equal to Hd minus T into Sd. So, in principle I can talk about T, which is the Tc should be equal to, so H naught minus Hd divided by, if I take it this side it will be S naught, okay. So, S naught minus Sd, right? No, okay. This you bring it this side, this you take it that side, Sd minus S naught, will it be? Why? This is negative, this becomes positive. So, T into S naught, this is right, this is right. So, you can see that this is what it is, and as a result this difference which is nothing but related to the omega. So, the larger the what is called the interaction parameter between the A and B, the more negative the interaction parameter is, the higher will be the Tc. So, the order disorder transition temperature would be higher if this difference is higher. If I treat a disordered structure as that where the interaction parameter is 0, because in principle we can take it as an ideal solution, it is a disordered structure, the A and B there is no preference, they are all sitting everywhere. So, I can call a disordered structure almost like a solution which always will have the interaction parameter as close to 0, and that is what we say that isomorphous kind of phase diagrams you get when the interaction parameter is 0, where liquid gives you solid, which is a disordered, chemically disordered, structurally ordered of course, but it chemically disordered. So, Hd basically is close to 0, okay, H of the disorder, whereas H naught is decided by the omega. The larger the omega, and this is negative and this is also negative, so negative goes off, so finally you get a positive number for Tc, isn't it? So, this is H naught is more negative than this, so that is why this is a negative number, and this is also less than this, so this is also a negative number. So, ultimately you get a positive value for the Tc, and the value of the Tc is again going to be decided by this to a large extent than this, because S of the disorder does not depend on anything, it does not depend on what is A and B, it is simply configurational entropy. If I am taking 50-50 let us say copper zinc, it has a certain value. If I am taking Ni3A let us say 75-25, it has certain value of configurational entropy. It does not depend on whether it is nickel or aluminum or copper or zinc, configuration entropy does not depend on that. So, you can see it is this omega which decides it, that is why in certain compounds the transformation occurs at a lower temperature, in certain compounds transformation does not occur until you reach the melting point. In copper zinc 450 is where it transforms, whereas in NiAl it transforms, the order disorder transition occurs at the melting point. When the solid is actually melting, then the disorder takes place, chemical disorder. So structural disorder and chemical disorder occur together in such a material. So this kind of things need to be understood. So everything is related to this. Okay, we will stop now.